Hello and welcome back to the lecture on applied econometrics. In this lecture, we are going to talk about the assumptions of regression models with non-stochastic regression. Now, this is essentially a summary of all the different diagnostics that we have been doing all throughout in the past, so many weeks. And we will do this, we will first summarize these assumptions for a non-stochastic regressor. So, essentially I told in the previous lecture that the regressors that we have been using, or the assumptions that we are making, that our regressor is essentially non-stochastic. Okay? And first we will talk about all the assumptions that we need to make for regression modeling when we are dealing with a non-stochastic regressor. So, let me write down the first assumption, and you are actually familiar with all the assumptions, because you actually have done that when you have done with functional specification, when you talked about multicollinearity, when you talked about heteroskedasticity, when you talked about autocorrelation, when you talked about model specification and so forth. So, all the different learnings that we had so far, it is going to be a summary of that. Okay? So, the first assumptions that we are going to write is that the model is linear in parameter, the model is linear in parameter and correctly specified Now, you know about what I mean here, right. So, when I say the model is linear in parameter, so that means that the parameters should not have any power, or it should not have any term that if I differentiate, that it remains in the equation. So, let me actually again sort of let us recap it. So, let us say y is equal to, we have an equation beta 1 plus let us say beta 2 x 2, and let us say there is a power beta 2, and then we have our error term. Okay. Now, in this regression equation, now if I cannot have this here, because then it is not linear in parameter, and this is a problem, because when I let us say differentiate, when I actually follow the least square method to estimate the parameters. So, what I do basically, I do this, I take partial differentiation of y with respect to beta 1 and beta 2, these are my parameters, right. Now, if I have a linearity in parameter, then what I will have in one equation, I will get my beta 1 vanished, in another equation I will get my beta 2 vanished, but that is if I have non-linearity, that is not going to happen, and then I will have, even after taking the partial differential, I will have this beta 1 and beta 2 present, both the beta 1 and beta 2 present in the equation, and that would be a problem, right. We cannot estimate the beta 1 and beta 2. So, it has to be linear in parameter. The second is, it has to be correctly specified, and we already know what it means. By correctly specified, it means that the functional specification has to be correct. So, if it is a log model in the y variable or the other x variables, we have to sort of ensure that we actually have the log variable, not the just the x variable. So, we have to take log of x, or if it is a quadratic, we have to take a quadratic. So, whatever be the functional specification, we have to sort of find that, and that we have already dealt in detail how to actually ensure that we get the right functional specification. The second point is that there has to be some variation, in the regressors. What I mean by that? So, if my x is my regressor here, and there has to, x cannot have just the same value for all the different observations. And why is that? Because I know that my beta 2, the regression coefficient, is summation x I minus x bar and y I minus y bar, and then I have summation x I minus x bar whole square. Okay. Now, if all my x is the same, so the denominator is going to be what? Denominator is going to be 0. Now, the moment I have my denominator 0, my beta 2 is going to be undefined. So, my regression, I will actually not, my software will not actually give me a output because of this thing. So, we have to have some variation in the regression. Now, a follow up of, let us say we can write 2.1. So, when we do a regression, we have to ensure that the x variables should not have, any, should not have an exact linear relationship, and we have already seen it, we have already talked about it in detail. Recall dummy variable trap. So, what we mean by x variables should not have an exact linear relationship. So, there can be some linear relationship, but it cannot have an exact linear relationship. So, the moment you have exact linear relationship, so you have a problem called collinearity, so which we have talked in detail in multicollinearity. So, again to recall what is that problem? The problem is, let us say you have a dummy variable, okay, and let us say you include the base dummy, and when you sum up all the different values of the dummy variable, so essentially for all the observations your DI is going to be 1, right. So, there is no variation in the DI. So, all your DI is going to be 1, and you remember that you have an intercept, and intercept let us say beta 1. Now, beta 1 the intercept, and it has, you can think that there is a variable multiplied with beta 1, and that variable is going to have a value of 1, okay, that is constant 1. Now, because for all the different values you will have this one constant here, and you have this DI, sum total of DI is constant. So, essentially your program is unable to distinguish, it will think that the same variable is represented twice. So, it is called a problem of collinearity. So, the moment you have exact collinearity, exact linear relationship, you will have the problem of collinearity. So, because your software or basically your regression equation, it will look like the same variable is represented twice. So, you cannot have a regression with that. So, that is what we call there cannot have an exact linear relationship. So, we may allow some linear amount of linear relationship, and that is what we have seen in the chapter of multicollinearity. So, this is our second assumption. Now, coming to the third assumption. The third assumption is the expectation of the disturbance term has to be 0. Okay. So, the error term, whatever error term we are having, if we take an expected value of the error term, it has to be 0. So, there could be in some observation your UI could be positive, in some observation your UI could be negative, but the moment you take expectation, you basically take an average, the average is going to be 0. So, that is something you have to have. Now, let us assume that your error term has some run in that, like some trend, some tendency in that. Okay. Usually the intercept term that we have, that takes into account that sort of any tendency or trend in the error term. Okay. So, the beta 1 that we have, that actually captures that tendency, but so essentially we cannot have any run in the error term. So, let us say we have our equation y is equal to beta 1 plus beta 2 x 2, and let us say I have a error gamma I, okay. And let us say gamma I actually it has some run, it has some trend. Okay. Now, in order to ensure that my expectation of u is 0, so if I take expectation of gamma I, it is going to give me some u, let us say some value that is not 0. So, which is not satisfying this condition. If in this particular case, since gamma I has some trend, it will the moment you take expectation, it is not going to give you a value of 0, you are going to get a value of u. Now, when you have this, so essentially you can write that you can actually represent gamma I is equal to some u plus ui. Okay. So, the trend that you have along with the error term which is random, for which this condition is satisfied. Okay. Now, if you replace this in this equation, if you substitute, so then what you will have is, let me use a different color, y is equal to beta 1 plus beta 2 x 2 plus u plus ui, all right. Now, you see your u is a constant term, it can very well go with beta 1. So, essentially what you write is beta 1 plus u, you have a beta 1 prime plus beta 2 x 2 plus ui. So, essentially the reason I sort of did this little bit of analysis is basically to show you that if you have any run, any trend in the error term, so it will be captured in the intercept term. Okay. And we really do not care so much about the intercept term when you do regression. So, it really does not matter, like if the beta 1 and beta 1 prime are different or whatever. So, essentially as long as this condition is satisfied, we are good. So, expectation of error term has to be 0. So, that is my third assumption. My fourth assumption my fourth assumption is the disturbance term is homoskedastic. So, skedastic. So, you already know about what is homoskedastic, what is heteroskedastic, right. So, let me write it mathematically. So, if I write sigma y square is equal to sigma u square. So, there is a constant variance. So, what it means is that each observation is drawn from a constant population variance. Okay. So, how is that possible? How is your variance for each draw is going to be constant? So, ideally it should be somewhere it is going to be a little more, somewhere it is going to be a little less, and in very rare occasion you can have something like this. But you remember the concept of double structure of variables. So, it is a case essentially of a double structure of variables. So, essentially it is when you write this equation, we are writing it before actual realization. Okay. So, it is basically before you actually, it is basically an expectation of the variance. So, I can write it like I can write. So, from the previous condition, I know expectation of error term, expectation of ui is equal to 0, and I know I can represent variance as expectation of ui minus u square, and if I sort of write it, so expectation of ui square minus 2 ui u plus u square. Now, this is going to give us, now this expectation of u this being 0, I will actually have only this will be this, okay, because of the previous condition I already have. Now, or I should actually write expectation of u, not the I. So, with this we can actually say that the variance of it is a case of constant variance where this is going to be sigma u square. Okay. So, this expectation of the variance is going to be constant, all right. Now, the next condition that you have already seen is a condition of autocorrelation is a condition where which we addressed in the case where we talked about autocorrelation, and that is there should not be any relationship between the error terms for different observations. So, covariance of ui and uj has to be 0. Okay. So, there should not be any relationship among these error terms. Okay. Now, sometimes it may happen when you look at your data, you can see or look at the error terms after you fit your model. So, you can see that the error terms might show some sort of positive tendency, or it can actually show positive, negative and positive and negative and so forth, and you already know this is a case of positive autocorrelation, or it can show some pattern like this, some zigzag patterns, and you know this is a case of negative autocorrelation, SCR, negative autocorrelation. So, we usually this is the we do not want this kind of situations to exist, right, and that is why you have to have, and in all these cases your covariance ui uj is not equal to 0, but you want to ensure that covariance of ui uj is equal to 0, because you do not want to have any pattern in your error term, right. So, now in the previous assumption and in this assumption, essentially what we are talking about, if you can actually take care of this problem, you can take care of the problem of omitted variable bias. Also, you can take care of the problem if there is any modulus specification or if there is any measurement error, right. So, by taking these problems into account, you actually take care of these problems, and when you have the assumption 4 and 5 right, so you can actually ensure that your error term is IID, is a IID random variable. Okay. So, we know the importance of IID random variable. So, our error term is IID random variable if I ensure homoskedasticity and no autocorrelation. Okay. Now, I will come to the sixth assumption, assumption 6, and the assumption 6 there says that there has to be a normality in the error term, normality in the error term. So, what I mean by normality in the error term and why I need my error term to be normal. Now, by normality of the error term, it actually is important. Okay. First, let me answer the y part. You remember the equation we have written when we wrote b2 is equal to beta 2 plus summation xi minus x bar into ui minus u bar by sum total of xi minus x bar whole square over all n. Okay. Now, you see that the moment you have this component, this because of this error term here, your B2 is getting a distribution, and the moment your u has a normal distribution, your B2 is also going to get a normal distribution. Now, why do I want, or in fact that is actually good for us, and why it is good for us? Because the moment I have my B2, it is having a normal distribution, I can apply things like t-test or f-test, right, which are essential, which are crucial for your to basically get your regression equation right. I mean, you have to sort of estimate the, you have to do the significance test, you have to do the confidence interval, you have to get the confidence interval, and you can get that only if you can run this t-test and f-test, right. So, that is why the normality of error term is really functional, because you can get a distribution for your B2. Okay. Now, even if, so usually the error term is normal. The reason is actually we need to go back to our central limit theorem, and it is a particular theorem by Lindenberg-Feller's theorem. So, Lindenberg-Feller's central limit theorem. So, what it says is that if let us say there are a lot of influences on a particular variable. Okay. So, on my error term there are a lot of variables of which I am not even aware of. Okay. So, they are influencing of, they are not present in the model, they are influencing from outside. Now, and as long as these outside influences are not very strong, my variable of interest is going to have a normal distribution. So, that means my error term will have a normal distribution. So, usually that is why we actually get my error term to have a normal distribution. Even if let us say there are cases where your error term does not have a normal distribution, let us say this is a case 1. Even if your error term does not have a normal distribution, if it is a IID random variable which is non-normal, even then you will be able to perform your t-test and f-test. Okay. So, you will be fine, t-test and f-test. And another case could be it is not even IID, okay, not even IID random variable, but if you have a very large number of observation, you can actually perform your t-test and f-test. Okay. So, essentially because your error term is either normal or it could be IID non-normal. So, in most of the cases this is not a very big problem. Okay. So, these are the assumptions that you need to ensure when you have your regression model with a non-stochastic regressor, and as you have seen, what I have done essentially I have just summarized all that I have been doing for the past few classes. So, with this I will end the lecture here, and in the next lecture I am going to talk about the same assumptions, but for stochastic regressor. Thank you.